Hello, welcome after lunch. I'm equally surprised as you that I'm here. Jakob messaged me yesterday at 10 p.m. Can I come over and speak because some of the speakers drop out? So it's a bit short notice, so please be gentle if there are some signs of not being exactly prepared. And if you were at the Matthias workshop yesterday, some of the things I'm going to talk today are kind of similar, but maybe a bit different take at them. My name is Michal, and because I have funky letters in my name, it sometimes gets rendered like that. And that's because I'm from this country, from northern part of Poland. And I really like this picture of from International Space Station because it shows my both current home. Because around 5 years ago, I moved to Sweden, and I work for a company, consulting company called Tredon37 or Tredon37, based in there. If you get the name, you get it. If no, it's. And today we're going to talk about machine learning and artificial intelligence in general. And quite a lot when you hear about artificial intelligence, especially in media, it's showed pretty much like that. It's evil, it's come over to take our jobs and our clothes, and it's wildly undefined. But the way I see artificial intelligence, it's a bit like this white rabbit that we're chasing, that at some point we define it as something like some sort of like artificial creation that will be semi-intelligent. But when we get to the point, we suddenly don't consider it artificial intelligence anymore. So let's look at one of the first computer, ENIAC, or yeah. They were designed to just calculate ballistic tables for artillery for US Navy. And back then it was considered like, computer brain, because it was making those complicated calculations much quicker. But right now it's just, for us, those are just like very simple trigonometric calculation. We don't really see it as artificial intelligence. Then in the 90s, we had like Deep Blue playing chess, and that was like the hallmark that if the computer beats human in chess, that's going to be artificial intelligence. And by now, the computers are like so capable that we can pretty much game of chess is solved issue. You can like put a lot of moves up front, like predict them what's going to be the best game, and it's we don't really consider it artificial intelligence. A few years ago we had Watson playing Jeopardy, and it was again quite a nice hallmark. Then a couple of years ago we have like Google DeepMind that played Go and won. So it's like, what's next? And probably recently you saw like 3 months ago the same crew beats professional StarCraft players in StarCraft. So another let's say bastion of human intelligence got conquered. But today we're going to look at a bit more simple way, and I'm going to talk about one of the simplest algorithms in the machine learning called linear regression, to basically show the process and maybe strip down the math down to like more developer-friendly terms to show you that maybe it's not that evil, at least in the form we're mostly playing with right now. So let's get to some like math basics. So one way of showing data is two-dimensional charts, when on the horizontal axis you have some parameters, let's say age, and on the vertical axis you have values for that thing. So for example, how much money you have in the bank for a given age or whatever. So yes, you have parameters, and this represents some value. And you can also show this data in like discrete values, so like point values on the chart. But if you like put a lot of charts in the one line, so they're so dense that you can kind of represent it in the form of the line, and you can call it linear function. And this basically means that for every value of the parameter, you have for every parameter you have some value. There are like no gaps in the thing. There's of course simplifications. We have like mathematicians here that probably want to kill me right now, but let's do it later. Kill me after that. And the linear function has two parameters, a or b, or a and b. And a is responsible for like what's pretty much the angle of the line. So the higher a, the bigger angle. And the b is responsible for like how much we shifted from the horizontal axis. So let's say if a equals 1 and b equals 0, then we start from the cross point, and the line is at 45 degrees, because for let's say using this example of money, for like every year you gain $1 or wherever. And another example is like when you a is bigger than 1, then kind of this line is going up faster. So maybe you're hired in Norway or other situation in life. And example of b begins 0 is like kind of the line starts already pretty well. So let's say you were born to rich parents or something like that. That's just going by this analogy. And in data science and machine learning, we use a bit different names for those arguments. Use W and B because it feels well with the terminology, that W are weights and B is bias. It's just good to know, but not really important for the case today. But if you're gonna read some documentation, you're gonna see more common those things. And today I'm gonna use example that I stole from Matthias Brandon-Winder. Hi, Matthias. And we're gonna predict the quality of wines using linear regression. And for that, I'm using a data set from a University of California. And the data set looks like that. It's a CSV file, but I open it in Excel for clarity. So we have a bunch of kind of like features of that wine, of wines, and how they were like what was the quality seen by I assume some kind of wine expert. So now, given that we have all that data, we'll try to like design algorithms that, given this all chemical parameters of wine, will predict how good of the wine is this, or like how well it will be maybe judged by some wine experts. So we have a bunch of values here, like acidity, residual sugar, chlorides, amount of alcohol, pH. And we're going to use this as an input, and our kind of output values will be quality. Let me get back to, where's my mouse? Here it is. Good. All right, so basically we will use linear regression to predict the quality of wine using the data thing. And I'm going to show this example using just one feature, because thanks to that we can show it in like 2 dimensions. If I use 2 features, we would need 3 dimensions. If I use 3 features, mathematics can handle this, but humans not so well if we have to do like 4 dimensions and more. So let's just visualize it in 2 dimensions for our own sanity. And basically, linear regression, in the most simplest way, is about fitting straight line into the data we have. And we have to find as good fitting to that data as possible. And one way of to do it is just calculate how bad it is, and then just kind of change the parameters of that line to minimize how bad we are. And the measure of how bad we are is a cost function. And this is mathematical version. It's not that hard of a math, but if you see this like sign, that sigma, people sometimes get already confused, like this is math, I don't want to have anything to do with it. So let's talk about it in developer terms, because this is for loop. So just let's look at the for loop. So for each of the data points, we get the difference between our prediction and actual value, square it up, and add all to the sum. So if you look at like mathematical version, it's like that. So if I visualize it, it would be something like that, that we calculate like how far away we're from each of the thing. Then we square it up, and it has, and the reason we use square is, I think there are at least two reasons. First of all, no matter if this point is over or above the line, by squaring we remove the sign. So if it's like the difference is negative, then by squaring up we remove the sign. And the second thing is like the more far away you're from the line, the more penalized it is, because like square just will make those values that get far away even more big. All right, so let's try code it up to until this point, and then we'll try to figure out how we can reduce that difference. So I have a code open somewhere here. Drop it on the screen. Let me just see if you can see those letters. Are they readable? Great. I'm just going to move here because I didn't see it here. Great, so I'm using F# for a few reasons. First of all, it's the better programming language, but I like C# too, don't get me wrong. I think C# is also a fantastic programming language. And one of the problems with I think F# adoption is that C# is such a fantastic language, because let's say in the JVM world, languages like Scala get such a good traction because, let's say, Java is not such a great language. Okay. And another reason I use F# because it has a bunch of cool features. And one of them I'm going to show you straight away, because I'm just going to load those things that are not that important, basically running some, including some packages I'm going to use. This won't work. Will this work? Yes, this works. Okay, so funny thing about working with F# that we have something called interactive mode. So basically I can highlight just a bunch of lines and run this line separately, so a bit like you can run Python. Right now C# you can also run in this way, but a few years ago it was novelty. I can also write stuff directly here in the interactive mode, so let's... And I have now in my memory X that has value 42, so now I can oops. Okay, I made some boo-boo, but don't worry about it, because it's not the most important part. So basically I'll be going like line by line, and it's very cool to running in this like exploratory mode. You can just write some code in the interactive mode, it does what you want, you put it in your code file, and you can just build it up, and then you can simplify things. So right now I'm gonna go to the CSV file that I show you in Excel, and I'm gonna load it uses type provider. Type provider is a feature of F# that allows you to load data that quite often comes from different sources, like there are CSV type providers, XML type providers, or SQL type providers, and that data that's kind of not organized and really not typed data can be turned into typed data. So I load those wine files, and let me just take the first row from that file. And now I can do something that we all .NET developers really like, so dot-driven development. I press dot, and now all the kind of fields in that CSV file are available for me through IntelliSense, because now it's kind of type data. So I can check, for example, what's the amount of alcohol in the first wine in our file. says 9.4, so when I get back to this Excel file, and it's actually 9.4, so kind of works. Great. So now I'm gonna chart all the data I have, because like when you design algorithm, you want to figure out, I'm gonna do linear regression, okay, but not all features probably line up linearly. So like, for example, the bigger acidity doesn't mean the bigger quality, or so on. So I'm gonna chart some data and look at some charts and see maybe what approach might say. So let's, I don't know, let's try with charting the acidity, or where's dot? So I don't know, yeah, acidity. And we'll see how it works. I use Google Charts, so I have internet. Yes, I do. So this doesn't feel like it's kind of set in a linear way. It's kind of arranged in a one block somewhere in the middle. So let's try some other features of this wine. I don't know. pH is somehow related to acidity. What else do I have here? Residual sugar. Let's try this one. Also doesn't make a sense. So me coming from like Central Eastern Europe, I'm gonna bet on a well proven part of drinking wine and see how this works. And I see some like promising direction, like. So I'm gonna try it. So I'm gonna go now with hypothesis that the wine is better if it have more alcohol. I'm not sure if my French friend will agree, but we're gonna try it with data. And good. So now when you do like machine learning and you have a bunch of data, you don't want to use all the data to train your algorithm. There are a bunch of reasons for that. One of them is like when you train algorithm on your data and don't have let's put it in the way. You want to have some data that your algorithm haven't seen during training to be able to check your hypothesis against on another group of data. Just to see if your algorithm is not trained only on data it's seen, and it's very specific to that data, but it will not generalize well to other data that it hasn't seen, because we want to also work well on new wines we're going to bring, and it's like, well, this is called overfitting. And it's kind of, the good analogy is like when you have, let's say, test, and your teacher gave you questions, like sample test question. You learned by memory all those questions and answer, but the teacher brings other questions to the tests that are just kind of on the same topic, and you don't know how to act. So it's more about learning how to solve the issue than memorizing the questions. So I'm gonna divide this data, and usually, like the good approach is to take something about 70–80% for training data and use the rest for your validation, and then you can like also do validation and test, but let's not go there. I know there's like 1,600 rows of the data set, so I'm gonna just take first 1,000 for my learning data and use the following 600 for my test data. So using F# and sequences, I'm just going to take first 1,000 elements to the first sequence, and I'm going to use them for learning data. And another one, I'm going to go to the skip data, to the test data. So now I can check that my test data has around 599. All right. And yeah, So now we're going to write our prediction model and cost function. Prediction model is very simple. It's going to linear function, so it's going to take x and multiply it by b and by w and adding b. So basically, I'm just applying this to every element of the of our collection. And cost function is the one I just show you. I'm just gonna take the difference, square it up, and sum it up together. So just make sure the code run. And I wrote some helpers to drawing charts, not necessary. Okay, so let's just test how my cost function works and how my prediction works, and charting just for like really stupid values. So I'm gonna assume that w equals 0, 1, and b equals this. So basically, it means that if wine has 15% of alcohol, I'm giving it a score 15 on the scale of 0 plus 10. So it doesn't make completely sense, but we're just going to run it to see what's happened. So I'm going to get a chart, first of all. That's my predicted values, and that's the actual values, because they're scale up to 10, and my thing is going far away. So we want that blue kind of line going somewhere through the red values. And we have also, I think, should have results of my cost function. Yes, it's 11. It says us absolutely nothing, but usually good cost values are somewhere below 1. And it doesn't really matter. It's all about minimizing that value. So now let's talk about how we're going to minimize that cost. And one of the ways to minimizing cost, and one of the common algorithms of doing this, is called gradient descent. And if you imagine your kind of three-dimensional space generated by those values w and b, and how much is the cost, because for all of this value, the cost will have some value. And for a equals 1 and b equals 0, the one I show as my first thing, those costs were pretty high, and we find the optimal line that finds that, but that's the cost is really low. So we'll have to find a low point in that bowl, and it's not always a bowl. It's probably going to be more like, map of Norway or another hill country. And gradient descent not always will find the deepest valley, but probably one of the deepest, or one of the close deepest. So it's not perfect algorithm, and it will also not always yield the same results because we put some randomity in it. But it's good enough for a lot of things. And basically, we're gonna try to find a way to go on the bottom. And the way it works, I'm gonna now again reduce it to one dimension, but we just do it separately for 2 or 77 dimensions, depending on how many we have. And for each of the dimensions, we have to calculate derivatives. That's the most mathematical words today. And derivative is change in cost for a change in weight. Let's say if I take very small weight, how much the cost will change. And it's, again, not really important to understand how it works, because there are libraries that will calculate it for you. But what it costs, if we're basically, the hill is still steep, we'll be making very big steps toward the bottom of the hill. And the closer we are to the bottom of the hill, we'll be making smaller and smaller steps. And it's all about for that, so we don't really miss the bottom of the hill. Because if we do a big steps, so the the size of the step we're making is called learning rate. We could miss the bottom of the hill. We'll never get there. And we want to have fairly small learning rate, but not too small because it would take ages to get to the bottom of that wall. So it's like learning rate is one of the something we call hyperparameters. Kind of parameters we have to decide when designing algorithm, and it's a bit of trial and error what works. And the more you do it, you'll get more intuition. What are the good values? All right, so let's try to code it and see how it's gonna work for this case. How am I doing time-wise? It's okay. We're going okay. Okay, so basically I use this derivatives calculation that I figure out on paper what are derivatives for linear function, and we're not gonna get into this. But I mentioned there's like a, for example, library called the diff-sharp that can do automatic differentiation, so calculate derivatives for you. You can use it. I actually had a version of codes where I use it, but because I learned yesterday, I'm here, I couldn't find it. So let's actually run to learning, and those are hyperparameters. I'm setting alpha is the learning rate. It's just some number, and step is like how many times we'll follow this repeat this procedure of like recalculating what the steps we're making, calculating the and for that we use also cost and so on, and yeah, we're just gonna repeat and chart the process. So it's gonna run the whole learning process. And the thing is, like, I couldn't figure out how to make those charts animated, so I just made a lot of them. So we start from like flat line going on the vertical, horizontal axis, and I wrote chart every 10 steps, so we should have like 15 charts. And you can see, like, initially I'm just going pretty fast, and it's going slower and slower by the time we're getting closer to those values. And last few steps is barely anything happening. So probably that's close to optimal value. So let's see what values I have. I have a, oops, no, it's probably W. Yes. And what are you doing? Oh, okay, I wasn't at the bottom. So yes, WB. Cool. So it's they look very similar, but not. So W is 0.26 and B is 2.69. So let's say we have, what's the good amount of alcohol for wine? 12%. I'm not sure if it's gonna work. Should work. So this 12% wine should have. Oh yes, because floats. F sharp is not very like it doesn't. It's not easy only if you don't do types properly. So that one should have 5.8 quality, or like if you round it up, should be 6, maybe. Okay, but now we want to test actually how well we're doing against the other data, so the data I have in the test value. And I didn't actually write any good code to compare how well we did values. I just wrote a chart that also kind of work. So yeah, that's a good feedback. I should probably write something to compare predicted quality of what we're showing instead of I mean, chart is nice because you show something, but yes. Cool, great. That's half-assed demo, but we're on it. Okay, so basically that's our learned model. This straight line going through our data, and we're still working like with one parameter. We could probably do like a lot of more dimensions. Just the math would get slightly more complicated. And now, as I said, you can get like value because you take your X alcohol level, and let's say it's 12%, and by that we get value 4.5. It's different than I predicted, but cool. Right. Let's try to do it in a different way, because you don't always want to write code from scratch. It's like you would write quicksort from scratch every time you want to sort something. When we don't do this anymore. And I think machine learning is also in that way that it's going to be more like a commodity we're going to use instead of science that's tough and everybody's scared. So now I'm going to use something cool in Azure that's not so new, and I think it's slowly getting phased out or doesn't have so much focus, but it's really cool to show out a few things. So it's Azure ML Studio, and it's kind of more like drag and drop clicky interface, where you can like drop a lot of things, like you use your data sets. I have my data sets with wine saved here. And you have different data inputs, data transformations. You can put like blocks with R language or like Python language, so you can extend it in a bit. And let's go through the process I kind of did when like F# writing code, but like click it through Azure. So we have our input data. I just okay, here's cool. So we can select columns that goes into data sets, and I only picked alcohol and quality because that's the values I use also in the demo thing, in the code. Now I'm splitting data in the same way we did in code. So basically, I have to, like Azure use different logic. I have to put percentage, so I calculate how much of the 1600 is 1000. So we get the same kind of way. So we're splitting data, and part of the data goes to the training block. And the other input to the training block is the algorithm we're using, so it's linear regression. For linear regression, you can also kind of set up like what's going to be the algorithm, and there's like there's least squares and there's gradient descent. I'm just using this because it worked better for me here. As I said, in those algorithms, there's like a lot of and some randomness going on, so the results may be slightly different. Then we training model, and then we score model, so we compare what we trained against the data that was set apart, and then we evaluate model to see some values. So I'm just going to run it now. It should take couple of minutes. It's like the lowest tier, that's free. So it's, let's say, not the most powerful machine, but also the problem is not the most complicated. So it just took a couple seconds. And what's really nice, you can like visualize data on every step. So if I visualize our data set, I see what we have as an input data. We have like histograms of data. So it's like first, you can have like nice look first at your data. Then when we select columns, you can also see what's left. We only left those 2 columns. Split data, so you can see 1 and second data set, but it's just going to be the same. Now after we train model, it's getting interesting, because what we get as a visualization, we get bias and alcohol. So those values, that's basically, alcohol is the W from our things. So it came to conclusion to a bit different number, a bit similar, but just it's going to be a more flat function. Now when it's core model, we can see water quality and what was the score we given. So we can like actually kind of visually compare. So we have like 5 here, 5.8 is going to be more like 6, 8 here, 5.4. So you can see like some are close, some are not so good. But we can look through it. Probably a good step also would be like to round those values again. And now when we evaluate model, we get some statistical information, which is like the mean absolute error, mean square, root mean square error is the one we calculated as a cost function in the example. Coefficient of determination is like another one. How good is this model? And I think this values doesn't indicate it's a great model. Yeah, that's a cool way of doing this, because now when you want to go, for example, to more dimension, we just will cut it off. Okay, I'm sorry. Please don't reload it. Please don't crash. Come on. Do I have internet? I do have internet. Okay, let's just... All right. So I can move that arrow. No. Can I move that arrow here? Yes. So basically, we don't remove the columns, and now we can run the same algorithms using like more additional data. So use the data about acidity and so on, and like more dimensionally. Like doing it in code is just add a bit of complexity, and here it's very simple. We can actually run it and see how acidity impacts the wine. It's probably going to take a tiny bit longer, but maybe not that long. Another cool thing about this that you can actually expose it through like web service. So make it as your wine classifier into the API with Azure. It's fairly easy. So it's not super powerful, but you can actually make some prediction model and set it, expose it to API, and it's quite decent and fairly simple. Yes, so we can see. No, that's not a one. You can see like coefficient of determination is like twice the size, so it's a bit better model with all that data, but still not even close to 1. I want to show, so see this one. Yeah, so no, even I want to see this one. So to show you that, you know, we have like much more weights right now, not only alcohol, but all the other things went into weights, and other things impacts the wine. So let's get back to the slides for a moment, if you can see them. No, you can't. Cool. So this experiment shows that probably there is more to wine than alcohol. But also, what happens is like this model is maybe not the greatest model to model this data set. Probably maybe something like that would be better data set. And like one of the way to get like more curved lines to fit the data is not use linear function, but looks, for example, polynomial functions. And one of the way to get polynomial functions, for example, neural networks. That would be like part 2 of that talk. But you also don't want to get like too good to be very specific for the data, because it's not gonna generalize very well. Since we're kind of in this .NET space, and I want to mention just two like other technologies to look at that are more like code-based, so not like this Azure clicky thing that's fun, but maybe not always usable in production environment. Two honorary mentions, like CNTK is a bit more similar to Python's TensorFlow. It even have Python API, but under pressure for like .NET community also made the .NET API. And it's a very good kind of like framework for machine learning. And kind of new player or new kid on the block is ML.NET. That's I think he has now 0.11 version, so it's not really a production release. There are a few very interesting things they do. There are some controversial choices they made, but I think it's good things about it's like written in .NET Core. It's like native to the whole .NET ecosystem. And there are very smart people working on that project, so I think it's probably where the future lies for doing machine learning on .NET. So that's going to be all from me. Thank you very much for struggling through those demos and everything, and have a great rest of the conference. Oh, of course I take questions. Or I can take them later. I'll be here a whole day, so thank you.